Uh, now, how can I do that? It's a nice talk. The title, I'll tell you, is Integral Lexicographic Codes, and it's a very strange talk, and it was rather funny. A week or two before the International Congress in Zurich in 1994, I should say I'd actually attempted suicide and damn nearly succeeded rather before that, but I was coming back to life again. It's amazing how nearly succeeding I got. But anyway, I won't tell that in public, but I don't mind telling it in private to anyone. Okay. Anyway, a week or two before the Congress, I gave a talk in Elwyn Berlekamp's game theory conference, which he conducted every 2 years or something. And my talk wasn't a success. Really wasn't a success. No surprise, because I was still suffering from clinical depression, and one of the biggest symptoms of that is insomnia. So I wasn't getting much sleep. Okay, so that's that. And then next day, I think it was, Richard Guy was chairman of the session. He's now 99, by the way, and still going very, very strong, much better state than I am. And he said, "John, the next speaker hasn't turned up. Can you give a talk?" And I said, "Yes." Now, that's because I always said yes when somebody asked me a question like that, because I rather take pride in my ability to say yes in such circumstances. And we were outside a pair of swing doors at the time. I said, "When?" And he said, "Now." Now, he said, and it was the nowest it had ever been. Namely, we opened these two swing doors, and there was a sort of aisle between two sets of seats, you know. It wasn't as deep as this room. It was about 15 feet to the front of the lecture room, and in that 15 feet, I had to think of a talk, you know, and so on. Well, I used to be very good at that. And the method is, well, my method was to think of what I call the golden oldie, a talk that I'd given several times and had always been a success. So I ran 23 of them through my brain. No, I thought it came straight to this one, in fact, I think. And by the time I got to the front, I was fully prepared. But I was still suffering, you know, from the effects of insomnia and a suicide attempt and God knows what else. I was in a hell of a state. So I gave this talk, and it was the great success that had always been and has always been since. And then, so you see, this is a sort of advertisement for the talk. It's worth spending a few minutes on it because I'm really very fond of it. It puts me in a good mood. And I was still worried about my talk to be at the International Congress in Zurich. And okay, well, let me tell you, it was a success. We came out at the end of that lecture, and a friend of mine, Aidan Bruin from Canada somewhere, was coming out. He didn't see me because I was concealed behind one of the swing doors I've mentioned. And he said, "That's more like the Conway we know and love." Well, of course, I knew he knew and loved Conway, so to speak, but I really needed to know that for two reasons. I wanted to know that my impression that the first talk was a disaster was in accordance with the facts, and then, which that told me. And the other one, which was rather nicer to know, was that this talk was more like the Conway we knew and loved, presumably a pretty good one. And then I had the crazy idea of giving this talk at the International Congress next week. And that was a bit difficult because what they ask you to do at these congresses is they invite somebody, a sort of expert in X theory, to give a talk on developments in X theory over the last 4 years. They have this sort of simple attitude that, that's the way everybody heard your talk or somebody else's talk 4 years ago, and is eager to follow up now, crazy idea. And so I was asked to give this talk on developments in sphere packing over the last 4 years. To my mind, no matter what X is, this instruction they had means give a boring talk. And I didn't like it. It sort of put me off right away. But one of the things that brought me rapidly out of my depressive state was the fact that I'd acquired a girlfriend, Penny. And Penny, one of the nice facts about Penny, as far as I was concerned, is, there were other nice things about her, but is that she never saw a rule that she didn't immediately want to see broken. And that made life quite interesting. So I said, do you think I can actually give a talk on this subject, which is very little to do with sphere packing, despite, under the same title, etc., and before 4,000 people? She said, yes, of course, go on, just give it, She pushed me forward, and okay, so that's that. I arrived, everything worked beautifully, by the way. We arrived in Zurich, and on the way to the Congress Hall, I happened to pass a sort of American-style drugstore, which had toys and things in it, and I noticed a small basket containing, as I later learned, 14 spheres, 14 expanded polystyrene spheres in sort of bright colors. And I thought, oh, I'm supposed to be giving a talk on sphere packing, so possibly they'll be useful, So I took them out. Then we went to a place where they were serving coffee and, cafe and kuchen before the meeting really started. And there were these small cups for the coffee, and each cup would hold 3 or 4 of these spheres were really quite large, much larger than the cups, but each cup would hold about 4 of them, or 3 of them at least. No, 3 of them is a more honest thing, if they just were squeezed in. And also, I was wearing a horrible jacket, which was sort of dirty white, probably because it was dirty, but anyway. It had large pockets, and I could put these cups with the spheres in the pockets, which meant that I couldn't take this jacket off because I'd already had an idea about how the talk was to go. And then, then we went up to the actual lecture room, which, by the way, was full of lots and lots of people, the entire audience, and doubtless some more, the entire attendance at the Congress, because the talk after mine was by Andrew Wiles. At that time, they already discovered the bug in his proof. The message of his talk, which came later, of course, was the US cavalry are on the way, it'll all be cured, I know what's wrong with it, and I know how to cure it, and so on. And so, but anyway, everybody wanted to hear it. So I was speaking to an audience of more than 4,000 people. And the way I started actually was quite funny. I said, what was it? I sort of apologized. I'd changed the title of my talk, hadn't prepared it adequately. So here I am at an international congress and I'm winging it, Anyway, that's rather nice. You can see that I had recovered a little bit of my bounciness, That was the start of my recovery. I came alive again. Okay, well, I'll tell you what the lecture is about. It's about integral lexicographic codes. Now, wait a moment. This is that kind of thing, so I don't need to have the transparency. Oh, it will be. Okay, now I will. Yeah. I'm just wondering which way around to put it. I think the best way I can describe it, especially since I've wasted a bit of time, is to talk about the lexicode C3.
No, we can't see it.
Can't see it at all. What on earth is this doing?
You can put a sheet underneath it.
Ah, okay. The trouble is, though, there's underneath it, yes, I see. Well, oh, there you go. I don't quite know what. Yeah, I can see, but I mean, what do I do about it? Never mind. The integral, the lexicode C3. Lexicode will mean integral lexicographic code. Okay, C3 is the code of the lexicode of minimal distance 3. An integral code is a code, a binary code is one whose digits are 0 and 1, and it consists of words of zeros and ones, strings of zeros and ones. An integral lexicode has digits that are arbitrary integers, well, non-negative integers. I'm going to change that later on. So, and lexi means lexicographic groups, and what that means is you use a greedy algorithm. So the very smallest number will mean non-negative integer for the moment. The very smallest number is 0, and therefore the smallest code word in a certain lexicographic order will be the all zeros word. Now the next code word must differ in at least 3 digits from every code word must differ in at least 3 digits from every previous code word. So if you think about it for a moment, or even if you don't, I'll tell you. The next code word must be this. In the smallest case, those 3 digits are 1. The lexicography is roughly the same as the lexicography of integers in the usual notation. With integers, though, the digits do not exceed 9, and there's no similar restriction now. So after that, the next one is obviously 222, and so on. And then we get n for every number n, and then after that, only after that, can they stick out means leftwards, into the 4th place. And now the 3 digits that I'm about to put after that one, let's call them A, B, and C, must all be different, because if 2 of them are the same, let's suppose they're the same as the number n, then it's too close to this code word that has 3 n's in it. Okay? So the numbers must all be different, and therefore the earliest case in which those 3 digits are all different is 1012. And then if you think about it, 1012 is at least a distance 3 away from all the previous ones. Then we carry on. Now we'll get 1 something if we're lucky. Can we get 110 something? Well, 110 is too close to 11. No, it's not. It's too close to the all noughts word. 1101 bound to be too close to something.
All one.
The 3 ones word, yes. 1102 is too close to 1012. But there doesn't seem to be anything wrong with 1103. And there isn't, in fact. You could just check. It's at least 3 digits away from everything in there. Now, I don't want to waste time actually doing this anymore. 1, 1, 2, 3, 0, 0, 0, 1, 3, 2, 1, 0, 0, 1, 4, 5, 6. I'll just show you how that 4, 5, 6 works. The digits in these last 4 words that we're talking about are essentially a Latin square. Never mind, defining it precisely. That really means that the numbers 0, 1, 2, 3 are forbidden from now on in the last 3 places. So it's really just about the same as if the integer started at 4. And then we have 1 and then 3 digits, at least 4, that are not all equal. Well, this is the word, it is, okay. So there are the first few words. Oh, perhaps I'll go a little bit further, omega steps further in fact, and get 0, 1, 0, 1, 2, 3. This is the next word after that. Okay, is that visible to everyone? Okay, let me leave that there then. Now I'm going to announce the lexicode theorem. Which is oh my, I should have turned this the other way around. The lexicode theorem with the natural definitions of vector addition. Let me just not write the word vector, but write the word plus, and scalar multiplication. Every lexicode is a vector space. Oh my, how did it fall? Where did it fall to? I can't see it. Sorry? Yeah, somebody can see it and I still can't see it. Oh yes, oh I see. Okay. Oh, that's the wrong one.
Another one.
Oh, it's there still. Okay. All right. So let's look at this and sort of see how it works. The sum of any 2 code words, they're coordinate-wise definitions. The sum of any 2 code words is a code word. So let's take, for instance, 0, 0, 0, 2, 2, 2, and 0, 0, 0. Well, being understood that everything that is to the left of what I write, that these 2 are code words, and let's add them.
You move the sheet.
Okay. Let's add them, and now push it up. So this is in C3, and this is in C3, so that implies that this is in C3. Well, of course, that was obvious, really. I mean, NNN works for all N. So let's do a more interesting one.
Can I suggest one?
Sorry? Yeah?
001012.
0, 0, 0. Oh, no, it's the 1 in front.
1012.
1, 2, yeah.
And then there was, what was it, 1103.
1103. Okay. So these are in C3. These are in C3. 2, 1, 1, 5 should be in C3.
I don't think it is.
Yeah, I know. So there's things wrong with this, but it wasn't very nice of you to point it out. Since I was just about to discover it for myself. We've got to ask for some, some way of correcting this. Now let's find the simplest correction we can. Oh my, I've got to put paper under this. The simplest correction we can get is to insert here none. And then, well, I suppose we can make it into a theorem again by saying sort of not every lexicode, and that can be a theorem again if we like. But still, I sort of thought this theorem was true at the time, and so there ought to be something rather better than this. And well, you see, this statement said with the natural definitions, and it's not quite clear what the natural definitions are. We can say coordinate-wise, and I want to say coordinate-wise. Let's turn this into what I'll call the lexicode question. And it sort of says, are there natural definitions, let's say, under which, I'll abbreviate which to WH, are the natural coordinate-wise definitions? Natural doesn't seem to mean anything, but if there are, it will mean something, I think. Oh, and there's a question mark here. And now let's sort of see what happens. I want to take a simpler case than the one somebody gave me. I want to sort of search the first case probably. Always, you know, if you can't begin at zero, begin at the earliest place you can. Where is the lexicode? I want to keep it on the board so that you can follow things. Is it up? Oh, I see. Oh, yeah. Okay. I think the earliest dubious thing is 1012 plus 222 here. Now those are in C3, and so 1, 2, 3. Is it really 1, 2, 3, 4? That's not the earliest case. Let's take 1, 1, 1 and 1, 0, 1, 2. Then we get 1, 1, 2, 3. Yes. Is that in the lexicode? No, because 1103 I think is in the code, and two things can't differ by. Okay, so that's an example. Now, okay. Look, whatever the definition of the thing is, it's supposed to be coordinate-wise. Oh, well, look, have a look at this. Take the all zeros word. The simplest case, you know, is this. And we're going to add those two words. These are all zeros where I put the dots. And then we get the all zeros word again. Oh, do we though? I don't know. Let's suppose 0 plus 0 is Z. And then this thing is, you know, perhaps I should have some zeros at the front here, is Z, 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 Z. So the sum of the all zeros word, if 0 plus 0 equals z, then this is a correct sum, but then this word is in C3. But every word of C3 begins with infinitely many zeros. So z must be 0. So, oh, there's a wonderful theorem. 0 plus 0 equals 0. I seem to remember that happening in the previous lecture about games and things. Okay, so we proved something. Okay, but look, what's happened? How can you prove things? What's the lexicode, what's it right now? Right now, the lexicode thing is a question. But you can't deduce things like theorems from questions. So it must be an axiom. And instead of saying are there, it says there are. And then instead of a question mark at the end, we announce it rather positive. Yes, there are. You know. Well, on the other hand, really, we don't know there are, so we should leave that question mark underneath. Anyway, let's explore the consequences of the lexicode axiom. That's really rather nice. You know, none of you was clever. I always think that grammatical rule is really annoying. None of you were, as my temptation to say, were clever enough to notice that a vector space is defined over a field, and the integers don't form a field. So, I mean, let's just sort of interpret this as module. One of those, I mean, whatever it is. A module is really a vector space. It's just not over a field. But
well,
anyway.
The natural numbers aren't a module either.
Ooh. Is there some kind of semi-module?
Well, instead
well,
of
let's just call it a what's it. Okay. Well, never mind. I'll come back to that in the middle. There must be some way of rescuing this thing.
Yeah. Instead of being over a ring, it's over a rig.
A what thing? What
a rig? You take away the you take away the negatives. N is for negative, so instead of a ring.
Has that term been used by anybody?
Yeah.
Oh, great.
A rig is a ring without negatives.
Rig module.
Okay.
And if it's not the identity, then it's a rung. Take the I away.
Okay. I've never heard of those, but thank you. I'll try and use them in future if I can keep my face straight. Anyway, so right. But so what have we done? I tell you what. Let's try and work out what the addition must be. So here is an addition table, we hope. And we've got that 0 plus 0 must be 0. It follows from that 0 must be the 0 of the rig, I think. Anyway, I suppose it does. Okay. And now, what's 1 plus 1? Well, I'm glad you asked. We go back to this argument that failed. The sum of these two code words is, I'll take another piece of paper. The sum of those two code words, what was it? 1, 1, 1 and 1, 0, 1, 2 is 1, 1. 1 plus 1, that's going to be temporary. and then 1 plus 2. And so that must be in C3. But then 1, 1, 0, 3 is in C3. And two code words are not allowed to agree in all but 2 digits. And therefore 1 plus 1 equals 0, and 1 plus 2 equals 3. Okay, so, whoops. 1 plus 1 is 0, and 1 plus 2 is 3. Good. And now,
Commutative?
sorry?
Is addition commutative?
Oh, I don't know. I really don't know. So I tell you what, let's do this the other way up. 1, 1, 1 and 1, 0, 1, 2 is 1, 1, 1 plus 1, which is 0. And this 2 plus 1 must also be 3.
If you put that on the screen, we can't see.
Oh, I'm sorry, yes. I take 1, 1, 0, 2 and 1, 1, 1, add them the other way round instead of the way round I did.
Oh.
And then we get the 2 plus 1 is 3. Oh, that's a very good question anyway. Oh, but now look, if 1 plus 1 is 0, and we multiply by n, then don't we get n plus n is 0 too? Well, I'm not sure. You were probably pretty sure that it was. You see, because it's not clear that 1 is the unit element of the rig. Okay, however, instead of multiplying by n, we can multiply by n over 1. Oh, well, it's not. Yes, it was easier if we remembered it was a field, but it's not a field. Anyway, it turns out that it really is true that n plus n is 0 for all n. Oh yes, there's a good theorem. Theorem 2. The characteristic of our thing is TWO. I can't say the characteristic is digit 2 because digit 2 is 1 plus 1, which is 0, and the character, anyway, never mind. Good. Now I'm going to move into slightly higher gear. What's 3 plus, what's 1 plus 3? It's 1 plus, oh, I'm still doing that, am I? 1 plus 3 is 1 plus 1 plus 2, which by the associative law, which I'm assuming, I'm a little bit worried about that, is 1 plus 1 plus 2, which is 0 plus 2, which is 2. So 1 plus 3 is 2. And it'll work the other way around. And 3 plus 2, there's a similar proof. 3 plus 2 is 1 plus 2 plus 2, etc., and that's 1. Good. Mm-hmm. Which way, lower?
Just lower, yes, please.
Okay.
Thank you.
Right. Now, we have here a 4 by 4 Latin square. That means I'm not allowed to put any numbers in the first 4 rows, in the later parts of the first 4 rows, not allowed to put any numbers, any of the numbers 0, 1, 2, and 3. So all these numbers are at least 4. It's sort of, you can repeat the argument here, increasing all of these numbers by 4. To discover that this thing, one's got to be really rather careful how one says this stuff. Oh, sorry. In this block here, let me sort of do this because I don't quite know how to say it. You get from here to here I'll call this upping 4. Okay, I'm sorry. You know, to get from here to here, you up 4. I don't want to say you add 4, because in the new sense of addition, what these numbers mean are 4 plus. We've got to find out what 4 plus, say, 2 is, and it's 4 plus 2, obviously. It's not obviously 6, but it is indeed 6. 4 plus 2 is 6. And there's a similar thing that happens here. This block is got by upping this one by 4. And then when you've upped, you know, if you up by 4 twice, well, I mean, we've just shown that upping by 4 in this part of the table, at any rate, is adding 4. It's going to be really rather awkward not knowing which kind of addition we're doing things in. And so I'm going to introduce the school convention that which says if you enclose anything in square brackets, it means do it in the old school book way that you learned. So what we just proved, by the way, oh well, never mind, I won't bother with that. But here we add 4 twice to get from here to here, and so this must just copy that table. Okay. And then the same arguments essentially show that you get from this 8 by 8 square to the next 8 by 8 square by upping by 8. Or adding, you know, adding an 8 in the school book sense or whatever it is. And there's a nice theorem which I rather like. You know, this it says theorem 2 to the n, but that's in square brackets. Theorem 2 to the n. Oh, theorem 2 to the k, I think, is better. If a little n is less than 2 to the k, and say big N equals 2 to the k, then little n plus big N, which is the same thing as big N plus little n, is actually big N plus little n, the way you did it at school. Okay, so theorem 8 says to add 8 to a number, less than 8, you just add it in the school book fashion. And if you think about it, or again, even if you don't, because I've thought about it a bit, that tells you exactly what addition is. You see, you add 8 here, and you you copy there. And now that tells you what the first 16 by 16 block is, and so on. Great. So we now know what addition is, and it is indeed this thing which I used in the thing that I used. I should obey these ancient grammatical rules. Things I used in the last lecture. Okay. Now there is something interesting though, namely we should get interested in the multiplication table. Now here there's a place where for the first time we have a meta theorem. And the meta theorem is that you can't prove that 1 times 1 is 1. And the argument goes take, I'm not going to write it down. It's quite tricky, but it's fairly subtle, but which makes it hard. But you might be able to hold it in your heads. You renumber the numbers. You rename the numbers, giving each number n times the value, the meaning that it had before. Where n is a non-zero number. You rescale, let's say, the numbers, and then if the unit before was 1, then the unit after is n, where n is any non-zero number. Or else I got that the wrong way around. It doesn't matter. I mean, so there was meta theorem 1, and meta theorem 1 says, I'll just write it here. Meta theorem 1. 1 times 1 might as well be one. Okay? You won't get any contradictions from supposing that 1 times 1 is 1. So, okay. 0 is already the additive identity of the thing, and so it follows that zero times anything is 0. 1 times n is n. Okay. What's 2 times 2? Well, I'm afraid I've got to scrutinize this for a moment. Oh yes, what 2 times 1, 0, 1, 2. I now know a little bit about it. 2 times 1 is 1, 2 times 0 is 0, 2 times 1 is 2, 2 times 1 is 2 again, and 2 times 2 goes here. Oh my. I'm sorry, I have to slip in a thing here. We we get 0, 0, 2, 0, 2, 3. You can prove that 2023 is in the code, and therefore 2 times 2 is 3. These proofs that things are in the code are really very easy. We met a few when we started it off. So 2 times 2 is 3. Okay, so there's 2 times 2 is 3. 2 times 3 is 2 times 2 times 2. That's not going to help. 2 times 3 is 2 times 2 plus 1. We can apply the distributive law, which is 2 times 2 plus 2 times 1. 2 times 2 is 3, plus 2 is 1. Okay, so 2 times 3 is 1. 3 times 3. 3 times 3 is 3 times 2 plus 1, which is 3 times 2, that's 1, plus 3 times 1, that's 3. 1 plus 3, 2. You don't need to follow this because, you know, you can trust me. I wouldn't deceive you, would I? Okay. It's interesting what happens. So I'm not going to give proofs from now on for a little bit. 2 times 4 turns out to be 8. And 2 times 5, 10. 2 times 6. 2 times 6. 2 times 6 is 2 times 2 plus 2 times 4, because 6 is 2 times 4. So 6 is 2 plus 4, and that's 3 plus 8, and 3 is less than 8, so 3 plus 8 is 11. So 2 times 6 is 11, by the way. And 2 times 7 is 2 times 6 plus 1, which is 11, plus 2. 11 plus 2 is 8 plus 3 plus 2, which is 9. etc. Let me tell you what happens with multiplication, which you can sort of roughly believe because it's highly plausible. We have a theorem. I'll tell you what it is. If n is of form 2 to the 2 to the something, it now has to be 2 to the 2 to the something, and little n is less than big N, then n times little n, each way round, is equal to its school book version. But n times n is the school book version of 3 over 2 times n. Actually, when I proved the corresponding additive theorem, I should have said if little n is smaller than big N, where n is a power of 2, sorry, where n is an open square bracket, power of 2, close square bracket, then little n plus big N is its school book version, but big N plus big N, of course, we already know is 0. So, okay. This is a rather interesting theorem. So, for instance, 2 times 2 is actually 3. But you know, I rather like to call it 1.5 n. So 2 times 2 is 3. 4 times 4 is 6. 16 times 16 is 24. That gives you enough to work out the entire addition and multiplication table. It's not immediately obvious. Let's take... Oh, let me tell you what happened with 4 4s. You see, I had a definition which told me, actually, in another way, exactly how to work out the multiplication table. And that definition was analogous to the definition in the surreal numbers. Perhaps I should better come clean and give you the real definitions. No, I won't come clean just yet. It's hard to come clean wearing this shirt. So, I had a definition, but I found it a bit easier to work in this way. You know, they weren't defined in terms of lexicodes or anything. And I was lying before the gas fire in my college room and working out these things. And what I did for 4 times 4 is I could prove that 4 times 4 wasn't 0 because, well, if I assumed that it was a field, which I didn't know, because 4 is not 0, and in a field there aren't 0 divisors. And then I could prove that 4 times 4 wasn't 1 times 1, because the equation x squared equals 1 in a field has at most 2 roots, and no, the equation x squared equals some equation has at most 2 roots, and if 4 squared were 1, it would, etc. And then I could prove 4 squared wasn't 2 and 4 squared wasn't 3. Yes, because 3 squared is 2 and 2 squared is 3, so 4 squared can't be either of 2 and 3. Then 4 squared can't be 4, because if so, you could divide by 4 and get 4 equals 1. 4 squared can't be 5, because then it would be 4 plus 1, and the equation x squared equals x plus 1 already has 2 roots, namely 2 and 3. But 4 squared equals 6, I couldn't find anything wrong with it. And so that was the morning. I tried to find something wrong with it. And then in the afternoon, no, I think that's wrong. In the rest of the morning, I supposed the 4 squared was 6 and worked out the entire multiplication table below 16 on that assumption. And it was all consistent. And then in the afternoon, I applied my horrible definition, which told me what it was, and eventually proved that 4 squared was 6. Ooh. I was occupied with this thing for about a week, which and it sort of seemed crazy and at the same time interesting. Now let me tell you, coming clean, it's the characteristic 2 version of the surreal numbers. So you don't distinguish anymore between left and right. Now for addition, that just gives the traditional NIM definition, this business about adding in characteristic 2, adding in base 2 without carry. And we've seen that's what it is. So the addition is the usual addition of games that are impartial, that have the same same legal moves for each player. This gives a new definition, which I call NIM multiplication, and it's like this. Now you let x, instead of xl and xr, you let x prime be the typical number less than x. That's the same thing. You see, that means that instead of what I was doing last time, which was x plus y, sorry, have I got this right? Now x equals x left slash x right. Well, now we've identified left and right, and so x prime is that, and so x equals just x prime, the set of all x primes. And in von Neumann's definition, each number is the set of all previous numbers. And then, okay, so every theorem you get for surreal numbers should have an easy sort of analog, or every concept an interesting analog for these things. But however, these things are really the ordinals, or to be more precise, they're in 1-1 correspondence with the ordinals. And the thing you get when you take a set of numbers, but the set of numbers really means a game. Let's consider the set 0, 1, 5, 6. That is the game in which the player to move, whoever he is, can move to either 0 or 1 or 5 or 6. It turns out that the sort of reduction procedure is that is what I call the MEX, the minimal excludant. 0, 1, 5, 6 is 2, because 2 is the first number we didn't say. Okay? Nobody had ever apparently written down this curious notion of multiplication before. Oh yes, by the way, what is our theorem at the moment? Well, I've lost the place where I'm writing it down. Axiom? Well, I'm tempted to call it a theorem again, because it is indeed true, but it's really quite a difficult thing to prove, especially if you don't know where it comes from. And so I'll leave it as an exercise. And it sort of says find. Oh no, prove. Well, okay, never mind what it says. So that's the talk I gave essentially at the International Congress on the last developments in the last 4 years in sphere packing. Now, what I actually did was quite funny. I first did this business of taking the spheres out of my pocket and pretending I was talking about spheres packing. And that was quite funny because I was reaching in, and eventually I produced 14 spheres, which built up into a sort of pyramid on the lectern before me, describing what happened if you tried to pack spheres in 0 dimensions, 1 dimension, 2 dimensions, 3 dimensions. And then I said, now I'm going to change topic for a time And some of you won't recognize the connection with sphere packing until the end of the talk. What I didn't tell them was that almost all of them wouldn't recognize the connection with sphere packing even after the talk finished, because there wasn't much connection with sphere packing. But there is a connection with sphere packing, really. This coding theory perhaps gives that hint. This is a kind of coding theory, and in coding theory, one usually, let's say binary coding theory, one usually uses the so-called Hamming distance, which is the number of digits in which two code words differ. We've been using something like the Hamming thing here, except that the digits are not binary. So we've actually been developing codes in a space that has a metric, and well, there really is a connection with sphere packing. If you take the greedy code of any given distance, well, of any given odd distance, say 2k plus 1 distance, then round each code word and put a sphere of radius k, then those code words don't overlap, and so it's a good thing. And the answer to this game, and by the way, it's a game as well as a, never mind, it is a game in the way that I was developing games in the earlier talk, and the answer to the game, the set of winning positions, is the lexicode. It's also the best way of packing spheres in that particular kind of space. So there was a connection with sphere packing, but I never told it to the audience during the lecture. By the way, that brought me completely back. You know, this was a tremendous thing. It was tremendous success. The Russian mathematician, I've forgotten which one it was now, famous Russian mathematician, gave a summary of the things at the Congress for his Russian colleagues who weren't able to come. It was not that they weren't able to come for the old reason that, you know, they were locked in Russia and so on, just because they weren't able to come. Some of them, they didn't do it. And then we had the party. And now I'll just tell a story which has nothing to do with mathematics at all. Well, except that it might teach some mathematicians to behave a bit better at parties. Namely, the mayor of Zurich gave us a party for all the people attending the Congress. Now, you or I would have a little bit of difficulty giving a party for 6,000 people, but the mayor of Zurich took it in his stride. And what happened is, there were long tables about 10 feet across, 30, 40 feet long, and the tables had stuff to eat on them and drink. And each of these tables, there were about 20 tables, and each of them had a queue of about 50 mathematicians. Or maybe there were 50 tables and each of them had a queue of 20 mathematicians. But anyway, it's probably those numbers should both be larger. And these mathematicians were not behaving very well. I don't mean that they were impolite or anything. The trouble was that they were too polite and also rather stupid. When the first four people in line, you know, A came in, he was the first person and filled his plate with stuff. Meanwhile, B, C, and D all waited behind him, whereas in front of him there was a lot of space. So B should have passed forward, you know, before A, and C should have passed, etc. And then four people could serve themselves all at once. And we were really infuriated by this, you know, lots of lines of tables. Now Penny, who has already told you, never saw a rule that she didn't want to see broken immediately. She walked to the front of one of these tables and sort of looked at the stuff on it. And then she sort of couldn't quite see what was on the opposite side, so she walked round to the other side and looked from there a bit more closely. And she spent a little time doing this until it wasn't clear that she hadn't been at the front of the queue. And then she filled her well, she got 2 plates, one for her and one for me, and brought them back. And then Walter Fite, famous group theorist who was at the meeting and standing near me, said, "I wish I had service like that." So I said, "Penny, you know." And she took the hint and went to another table, of course, and filled a few plates of food with that. And then she tapped one of the waiters who was replenishing these tables from big sort of silverish trays. She tapped him on the shoulder, and he just gave her, you know, she took the tray off him. And then she could carry much more, but really the tray was rather hard to carry for one person. So she went and found another young woman about the same size, and they stood on opposite sides of the tray and carried it back. And of course the message had got through. These mathematicians weren't entirely stupid. The message got through that if you stood near Conway, you got fed. And so that's how I sort of thoroughly came back to life again at the International Congress in Zurich. Now I'm going to stop. Okay. Thank you. At the end, I suppose it is. You can declare formally that it's...
Are there any
Oh yeah,
questions?
questions.
I think
Nope. Oh yes.
I'll ask. I'd actually seen this bit of a description of your multiplication on the natural numbers in this case. There seems to be no easy way to describe it. Or is it the sort of the surreal base 2 version? Does that end up being?
Yes. Well, let me actually show you the definition. In a way, it's this does not tell you what the answer is. It is that xy is defined to be, oh yes, x prime y plus x y prime minus, really it should be, x prime y prime. Now x prime and y prime range over the numbers less than x and less than y respectively. Minus means the same as plus, but it's logically is minus. And this is the analog of the surreal number definition. That's the definition I was talking about. What that amounts, you see, suppose xy were equal to this thing, then x minus x prime times y minus y prime, well, if the distributive law and various other things held, would be 0. To say that x minus x prime times y minus y prime is not equal to 0, let me put it the other way around, is equivalent to saying that xy is not equal to any one of these things. So we define it to be the smallest number. In surreal number theory, everything is the smallest thing it could possibly be. So xy, we want if two things are non-zero, we want their product to be non-zero, which boils down to saying that if x is not equal to x prime and y is not equal to y prime, then this product is not 0. That is to say, xy must not be any of these. And then the simplest thing that is not forbidden is obligated, is demanded. That's a saying of, I believe, Schiller. What is not forbidden is necessary. Some saying like that. Of course, it's in German. Yes.
Are you saying xy, in multiplication in particular, it needs to give you the smallest thing it's allowed to be, or any definition gives you the smallest thing it's allowed to be?
Well, yes, but
I think we should be kind to the
Oh, yes,
startups
of
of the
course.
Newton Institute. They normally would like to lock up this room at 5. And when I said I don't think anyone has any questions, I meant no one should have any. So you can still ask questions, but outside.
I hope I've switched this off.